All right, we're going to go into more detail for several more of these compounds when we look specifically at how ARIO relates to the pKa values of each of these. ARIO represents factors impacting pKa. The more electronegative the atom, the more comfortable it is with the electrons, and the greater in size the atom, the more comfortable it is with the electrons, or the more stable the conjugate base. Resonance is the second factor. So once you form that conjugate base, if those electrons are able to delocalize or move across different parts of the molecule, it makes for a much more stable conjugate base. Next, we have induction. Inductive effects of electron donating or with electron drawing groups are going to impact the pKa value. Specifically, if we have very electronegative groups near where that negative charge is, there's going to be a pull of electron density stabilizing the negative charge. And last, we have the orbital. So that is the specific orbital where those electrons go once the compound is deprotonated. We have sp hybridized orbitals, sp2, and sp3 hybridized orbitals that we'll talk about on the final slide. All right, first let's look at atom electronegativity and size in more detail. So this table is taken from Wikipedia. It has the specific values for electronegativity within the table. Within organic chemistry, we're really focused mostly on compounds in this area. Carbon, nitrogen, oxygen, fluorine, the rest of the halogens, and then sometimes silicon, phosphorus, and sulfur. So looking at electronegativity, as electronegativity of the atom increases, so does acidity. So let's start with methane, which has a pKa of 60, and compare that to ammonia, which has a pKa of 36, and finally compare that to hydrofluoric acid, which has a pKa of 3.2. So notice the decreasing trend with our methane. We have a pKa of 60. For ammonia, we have a pKa of 36, as indicated here on the table. If we look at water, so an oxygen with 2 hydrogens attached, we have a pKa of 15.7. And for hydrofluoric acid, our pKa is 3.2. So as we get more electronegative on this row, acidity is going to increase. There's also the trend that size and acidity both increase as we move down the columns of our periodic table. So looking at fluorine, we already said that hydrofluoric acid has a pKa of 3.2. In comparison with hydroiodic acid, that has a pKa of -10. And you can fill in the gaps, so hydrochloric acid and bromic acid have a pKa between that around -8. So again, as the size of the atom, which in this case will be the conjugate base, as the size of our atom increases, acidity also increases. Next, let's talk about resonance. So I've selected a few compounds from the table: sulfuric acid, acetic acid, phenol, and ethanol. Sulfuric acid is the most acidic, followed by the acetic acid, followed by phenol, and last, the ethanol, which is the least acidic of the compounds that I've selected. So looking at these, we're looking at the stability of the conjugate base and the resonance potential that has. Let's look at the mechanism showing formation of the conjugate base. So if we're using sodium hydroxide as our base, the hydroxide anion is going to take the most acidic proton of these compounds, deprotonate it to form its conjugate base. In this case, we have sulfur, we still have an OH group, and now we have an oxygen, and that oxygen was deprotonated and now has a negative charge. If we deprotonate acetic acid, we'll take the electrons from our base, attack and form a bond with that proton. These electrons will move to go to the oxygen atom, and we will form our conjugate base. This oxygen gained electrons, it now has a negative charge. And for our phenol, we have these electrons going to take that proton. The electrons in that oxygen-hydrogen bond go to sit on the oxygen, and we still have our aromatic ring. And now our oxygen has a negative charge. And finally, for our ethanol, these electrons go to take that proton. Those electrons go to sit on the oxygen atom, and we now have oxygen with a negative charge on it as well. Notice the common trend in all of these cases. Oxygen has a negative charge on it. So resonance is all about electron delocalization. So where can these electrons go? However, there are different ways to show this, so we don't have to just show that. There are different representations of this because these electrons can move around. So if we move these electrons from atom to bond, then we would need to move these electrons up to the oxygen because we don't want to overfill the octet of that sulfur. So when we draw this other resonance contributor, now we have a negative charge on the oxygen. That was a double bond, now it's a single bond because the electrons from that bond moved up to the oxygen. That's single bonded to sulfur. We still have our OH group there. We still have our double bond there. And now this is our double bond. This has one additional resonance contributor where these electrons on the oxygen can move back down to reform the double bond. And then we can push these electrons up to this oxygen. So now we've got a oxygen double bonded to sulfur. We still have our OH group. And now this is a single bond with a negative charge on it. And this is still the double bond. So in this case, we have 3 resonance contributors where a negative charge is on an oxygen for all 3. So this set of resonance contributors, this electron delocalization, is more prominent than the next example. So for the next example, we have 1 additional resonance contributor where these electrons can move to form a double bond, and these electrons can be pushed up to the oxygen. Drawing this resonance contributor, we now have a carbon single bonded to an oxygen with a negative charge. We have that carbon still attached, and now we have a double bond oxygen there. So this is the other resonance contributor. In this case, we have a negative charge on 2 oxygens. Oxygen is an electronegative atom, so that definitely lowers the pKa value quite a bit, just not as much as if it was on 3 oxygens. This next example is interesting because we actually have the most resonance contributors for this one than the other. So if we look at these electrons, we can move these electrons down here, and since this carbon is not sp3 hybridized, we can move these electrons to here on our ring. So our next contributor, now we still have our aromatic ring, so 6 carbons in the ring, and now we have a lone pair and a negative charge on that carbon. We still have a double bond here and here, and now we have also a double bond there connecting the oxygen to the ring. From here we can move the electrons around the ring a little bit more, so these electrons go there, these electrons go there to this carbon to give us our 3rd resonance contributor. Now we still have our ring structure, our negative charge moved to this carbon. We still have a double bond right there. We have a double bond right there. And we still have our double bond oxygen. Finally, for our last resonance contributor, these electrons can move from atom to bond. And these electrons can move from bond to atom to form our final contributor there. So this is interesting. Again, like I said, this has 4 contributors, which in comparison to 3 or in comparison to 2 is more, but the pKa value is significantly higher. So this proton is less acidic. The reason why is because of what we talked about before, the atom effect. So oxygen is much more electronegative than carbon. So when the negative charge is only on one resonance contributor, where we have the oxygen with the negative charge, this is the contributor with the most significant impact. Although it is good and allows more stability that the electrons can move around and be on carbon, carbon is not as comfortable with that negative charge. So electron delocalization helps, and we'll clarify that by looking at this because this has zero potential for electron delocalization, but it's much better if the charges are distributed to the appropriate atom. All right, for this one, this is the easiest one. There actually is no resonance contributor. This is the only resonance contributor. This has a pKa value of 16. All right, let's move on to the inductive effects. Induction is the pull of electron density. Induction is the pull of electron density, but this is not talking about movement of electron density via resonance. So looking at the conjugate base of this compound, if we deprotonate, we'd have an oxygen with a negative charge. And now we've got this carbon here with 3 fluorine groups on it. These have zero impact on resonance contributors. So this does have a resonance contributor. These electrons can move there, those can move there, to give us this compound. So we've got 3 fluorines. But fluorine does not partake in these two resonance contributors. The fluorines do pull quite a bit of electron density. So those fluorines are all pulling electron density from the area of the molecule with the negative charge on it. Since it's got that strong pull of electron density, it stabilizes that negative charge a little bit more, making this carboxylic acid much more acidic. So inductive effects can vary in terms of how close the electron withdrawing group is. Before we move on, I want to draw one more compound. So if we have a similar structure where we have our OH group, and instead of having 3 fluorines on this carbon, let's say we had one more carbon and we had 3 fluorines on this carbon. In this case, the pKa value of this would definitely be higher than the pKa value of this compound here. So for the pKa value of this, I'm just going to take a guess and guess this to be around a value of about 2. The reason why is because these fluorines still have an inductive effect. They're still withdrawing electron density. However, since they're further away, it has less of an effect. Another example showing the impact of proximity of that electron withdrawing group. So we have a nitro group on an aromatic ring, and we have a carboxylic acid functional group on the aromatic ring. So drawing this conjugate base, got our electrons here. If this carboxylic acid is deprotonated to form the carboxylate anion, and we still have our NO2, there is zero resonance potential for these electrons to move into the ring. So these electrons can move here, and these can move here, but we cannot move electron density into the ring. So in terms of trying to pull negative charge from this area, this electron withdrawing group is pretty far away, which is why this pKa value is 3.4. Here we also have an aromatic ring. This can pull a little bit of electron density, but significantly less than if we have an electron withdrawing group on that ring. That puts this pKa value at 4.2. If we have an electron donating group on the ring, that also has less of an impact because now we're not pulling as much electron density anymore because our methyl group is donating a small amount of electron density into the ring. Finally, we have an example of our compound acetic acid, which is the least acidic of these. And in this case, instead of an aromatic ring, we have just a methyl group. We essentially have nothing pulling electron density to stabilize that negative charge via induction. All right, finally, let's look at the orbital where that pair of electrons goes. So if we deprotonate this proton and have our deprotonated alkyne, we still have our HC and we have that triple bonded to a carbon, which now has a lone pair and a negative charge. These electrons, so this lone pair of electrons, reside in the sp orbital. Since the sp orbital is 50% s orbital, s orbitals look like that, and p orbitals look like that. So this is a p orbital, and this is an s orbital. Since we have a combination of these two, it is 50% s orbital and 50% p orbital. That higher percent s orbital means that these electrons are closer to the nucleus of the atom. So they're closer to the neutrons and protons that make up that atomic nucleus, which means that it is more stable than electrons being far out in a p orbital. So in terms of an sp2 hybridized carbon, that would be this carbon right here. In that case, we would have two p orbitals and one s orbital. So we'd have 33% of each, which means we actually have 66% of the p orbital. So 33% of the s orbital and 66% of the p orbital. So looking at this conjugate base, if we deprotonate this proton here, that means we still have our double bond, we have our lone pair of electrons, and we have a negative charge. These electrons are in a hybridized orbital, an sp2 orbital, which is 66% p orbital, 33% s orbital, meaning those electrons are a little bit further away from the nucleus of the carbon atom. Now, there's no resonance potential on here, even though usually if you see a double bond and a lone pair of electrons, you might really want to write out some resonance structures for this, but there's nowhere for these electrons to go. And finally, for this last one, if we deprotonate our propane, puts a negative charge on that carbon there, there's no resonance potential. It's in an sp3 hybridized orbital, which means we've got 3 p orbitals and an s orbital. So 75% p orbital and 25% s orbital, which means we have the least amount of s orbital, which means that these electrons are furthest away from the atom's nucleus. So I'm going to end just by showing this pKa values table. It'd be good to just simply study this, memorize a few of these, and know how it relates to others. So some things that'd be good to memorize starting out would be the most acidic hydroiodic acid and least acidic propane or any sp3 hybridized alkane functional group. It would also be good to look at alkenes and know that if you have an sp2 hybridized carbon, the pKa value is significantly less than sp3. And alkynes, knowing that this sp hybridized carbon is significantly more acidic than an sp2 hybridized carbon. Think about resonance applications. Even though this is on an sp3 hybridized carbon, any guesses as to why this is nearly as acidic as this? All right, looking at the conjugate base of that, sometimes that helps. If we have a lone pair of electrons here. The reason why this is even slightly more acidic than this is because this has resonance stability. So these electrons can move here to form the double bond. These electrons can move here, and you can have another resonance contributor for that. So I recommend that you continue to go through this table and just look at how all of these relate. So think about, for example, one more thing, the conjugate base of this. So if we have this, and we deprotonate this proton here, we have a negative charge on this carbon. Even though, again, this is on a carbon, this has resonance stability, and better yet, one of the resonance contributors has a negative charge on an oxygen, which is much more electronegative than a carbon. Hopefully that helps. Let me know if you have any questions or you need clarification on anything here, and I'd be happy to answer. Thanks for watching, and I'll talk to you later.